light amplification through the stimulated emission of radiation laser. Shout out to Mr. Cottle, my 4th grade teacher who taught me that acronym. And hey, back then, you know, adolescent boys, we were super into Teenage Mutant Ninja Turtles. That cartoon was reasonably new, and I distinctly remember drawing an anthropomorphized kangaroo. So picture the muscle body of Arnold Schwarzenegger with the head of a kangaroo holding a laser rifle. I was captivated by the technology. I thought it was the coolest thing ever. So fast forward 35 years, and I am stoked to finally have my very own laser, what you're seeing right here. But with all that age, all those years, comes a little maturity, and I'm even happier that this is a tool of creation, not a tool of destruction. I'm much more fulfilled making things than breaking them. So awesome, awesome technology that we now have at our disposal, and that's basically why I agreed to review this unit, because laser cutters have just in the last year or less cleared a bar that had not been cleared before as far as the availability of DIY machines that are functional and do the job. Back in 2010 to 2014, I was doing my master's degrees, architecture and then digital technology, and I had access to a lot of fancy machines. And more often than not, I used the laser cutters instead of the 3D printers. And if you are a maker, you might start to seriously consider getting a laser cutter. It's a very effective tool which you can do a lot of great things with. So if you're going to buy one, please follow the link in the description down below. This is the first ever affiliate link that I've ever had on this channel because I like to appear unbiased. And I think that doing an affiliate marketing thing makes it look like I have moneyed interest, so I'm not going to tell you the truth. But I promise you, I will not temper my words. You're going to get the unfiltered opinions from this video. But I was not going to be given this machine unless I agreed to sign up for the affiliate marketing program. And it's all the same price. It's $2,000 everywhere you look on the internet. So if you're going to get it, follow the link, please. All right, enough looking at me and enough talking without looking at the machine. Let's get a close-up of just what I've unboxed here. And that's as far as I've gotten. I just took this thing out of the quite large box. You can see that it came in. And it's not too big. Whoa, that was good. But yeah, this came very well packaged. There were 2 nylon Velcro straps that were holding everything all together, so it's not going to get damaged in shipping, and there's really nothing that fragile about it to begin with. This here is the core of the whole machine. This is where all the action happens. This is it. And this part alone, I looked it up, and cost more than $1,000. So a 40-watt diode laser array is basically what's in here. So let's kick off this video by taking this thing apart and seeing what the business end of this machine is all about. All right, I've partially disassembled the laser head, and I don't want to disassemble it any further because I'm pretty sure if I go any deeper, I'm going to break something. If we look at this on its side, we can see this unit here, which to me looks like an actual laser pointer laser. You know, this is going to be like, what, a 1-watt laser. You could combine a bunch of these with mirrors and make a cutter, I guess. But the point of this is for visual referencing so that the operator of the machine can see where this is going to go. So we'll see. I think that's what that is, though. And then this right here looks like an infrared sensor to me. I think this is the unit that detects if you have a fire happening inside the cabinet. So this PCB here kind of operates the diodes themselves and provides this extra functionality. All right, we can see these little chips or something buried in Celastic. 1, 2, 3. There's another one behind the wire there. 4, 5, 6, 7, 8. You see that sort of diagonal array? So those are going to be 6-watt laser diodes. Each of those is 6 watts. And if you multiply 6 times 8, you get 48 watts. So I guess there's some loss here in the mirror assembly that we're going to talk about, but total is 40 watts when it's all said and done. So how do 6 diodes mounted there end up coming out of the tip right there? Over here, I've drawn the beginnings of the array, and we can see the first diode. Well, there's just 3. I didn't, there'd be 8 of them. But anyway, the first of them here is bounced off this mirror, bounced off of that mirror, and comes popping out of the tip of the laser cutter head down here. So the second diode is going to have to come down here, and we gotta miss this mirror. Let's come down a little ways, a little further, so that beam Okay, it misses that mirror, so we didn't collide with that mirror. That's good. But hey, how do we put a mirror here without blocking this light? I guess you could put a translucent mirror, so it's like a one-way mirror, kind of. But one-way mirrors still block, like, I don't know, what, half the visible light, or half the whatever frequency wavelength of light you have. It's going to block about half of it trying to go through there. So you don't want to block that. So what you're doing instead is putting a tiny little corner of mirror there. Just a tiny little corner. So it comes to the corner so that this beam here just barely misses the mirror. This one here hits the mirror and goes down. So they're parallel beams. Very close together, but not exactly one on top of the other. Okay, and you're going to do the same technique with the third one here. Hit this mirror, come on down, come across, hit just the corner of this next mirror, and head on down through there. Oh, whoops. Didn't mean to do that. Okay, so what you end up with is obviously a beam of light, which is a laser. It's all parallel rays of light, but it is much thicker. So it's going to be 8 times thicker in the case of the actual unit than any of the individual 6-watt diodes themselves. And so inside of that block, that crazy CNC block right there, you can see the CNC telltale marks. So they've done a lot of fancy work to get their mirrors happening really, precisely deep inside there. I wish I could break it apart. Maybe I can contact Xtool and they'll send me a factory second, a broken one. Anyway, let's get this thing back together and installed into the machine so that I can actually start using the machine and make some things. There are a couple of items I forgot to talk about. First of all, this slot. Weird little thing. This looks like 2 magnets and 2 screws to hold the unit in place. There's a PCB right there, printed circuit board. What on earth could this be? I think it's the bed sensor. And the reason I think that is because there's some writing up inside there that says BL Touch. Hey, I've got BL Touches. That's this sensor from the 3D printer world from a couple years ago before we were tapping the nozzles on the beds themselves. And these were pretty fancy, pretty great little units. And you can see right there, BL Touch by Ant Collabs. The next thing to talk about is this tip. And I forgot to mention that after the light bounces off all those mirrors and it all is, collimated and coming straight down through this tip, what's happening is there's a lens that focuses that laser to make the width of the laser beam just a little bit narrower. Now, the light is going to stop becoming parallel once you use a lens to focus it. It's now going to become angled. So you have to get that focal distance just right. So there's going to be some futzing around with the distance of the cutter head from the material just to get that beam to be as tiny as it possibly can be and get your best cut. This unit here, which came in the box, is going to be the air assist unit. So we've got the tube, the air tube that plugs right into there, and then that gets routed such as it will inside of the machine, and then gets plugged into right there, like so. And after it goes through there, we can pop this little cover off, and we can see that it goes all the way to the nozzle. I don't know what to call this. That's the laser cutting head. That's the lens right there. And it keeps the lens from getting fogged up with soot because, this is cutting with fire, basically. So you have fumes coming off of the actual cut, and that could really mess up the glass right there really quickly. So the air assist is kind of important. It's interesting to me that there's even a cover on this. I don't know why they would do that. I mean, that's a fancy little CNC'd part, so it must be important. I can't think of the issue, but yeah, that makes it look nice anyway. It looks nice and contained. So this right here is a key piece of kit because you do not want to be in the same room as this thing, which is literally with fire burning holes into your material, especially if you're cutting some like toxically glued together plywood or something. There's all kinds of nasty fumes. So you got to vent those fumes, and hence this thing here. I'm gonna have to do something to hold that up to the ceiling. So that's an issue that I have to solve before I can even start using the machine. This air assist unit is mounted on these really fancy rubber feet that allow it to jiggle a lot. So I think that'll help with the noise reduction and anti-vibration and stuff. But you can see just a very thin little column of some squishy rubber. course, we have our power supply and all the cables. We've got these boxes, user manual. And in here, we've got, oh, I don't know, interesting, some stuff. Huh. Oh, these are sample materials for cutting. This is going to be glass, not plexiglass, because it's clear, and I do know that diode lasers cannot cut through transparent plexiglass. We've got some dog tags, some actual stone. This will be a fun one, like a coaster, I guess, because they've already put the rubber feet. And I think this is just some fancy paper, leather, plywood. That's not too thick. It's pretty thin. And we got some plexiglass, which is also pretty thin, but yeah, acrylic. The final box is this one here, and it sounds like it's got some tools or something. Click these into the bed here, and they stick down into the hole, and then this clip holds down whatever object it is that you're trying to cut. And we got some felt blocks. Turning the air assist unit upside down and opening the door here, that's the filter. So these thick felt pads are replacement filter cartridges. We got some grease, probably for the motion system. These look like locating dots. That's interesting. What would these be used for? The stickers are to be attached to the working area of X2S1 to facilitate the position shot function. For details about how to use them, see the instructions in Excel Creative Space XCS on a mobile phone or iPad. Roger that. And we got our little toolbox, it looks like. So these are actually keys. Do you guys see the little key logo? So they go here into the back of the machine in the key slot. And I guess the machine won't run unless that's plugged in. And here is the bed probe. So you just sort of slide into place. Remove the rear limit piece and the sticker before use. Okie dokie. And now, according to the user manual, I just plug the laser head in and then mount it in place with a couple of screws. So there's a stop right here, and as the adjustable Z height is activated, it goes up against there, which deploys the probe, and then I guess it just pushes. Maybe there's, like, it pushes on the edge or something like that to retract the probe. Fancy schmancy. I've got the machine turned around so we can look at the back side. The user manual tells me to plug the hose here from the air assist into the top hole with the puff of air marking. But hey, why don't I have a hose to go to the fire suppression? The fire suppression unit is an add-on costing an extra $170. So the machine also comes with this long USB cable for plugging into a laptop. Lastly, and most importantly, here at the back of the machine where all of the electronics are located is the e-stop switch. If you guys have never seen one of these before, they're pretty fun to play with. I've got the smoke ventilation hose wired so that it's closer to the room ventilation. Quite a bit of air gets sucked out of that vent, so I think this will be sufficient to exhaust all the fumes out of the room, but I'm going to have to come up with a more permanent solution later on. And yeah, everything is plugged in. This thing is ready to go, so if I just reach back here and flip the switch, let's see what happens. It's homing the machine. All right, the machine is set up and it's ready to cut the first job, which means I need to figure out what my first project is going to be. And I'm looking at this material selection that the company included in the box to get an idea of what the company, the guys who made the machine, are telling me that the laser is capable of doing. I'm very intrigued by the fact that they sent these glass plates. These are clear. So I highly doubt we can cut through these glass plates, but we can probably etch them. And same with the dog tags, the metal dog tags. A 40-watt diode laser is not going to be able to cut through any real thickness of metal. I did see a video of a guy with a 70-watt diode laser who's cutting through some pretty thin metal, so that starts to get into that capability at 70 watts. But yeah, it's a diode laser, and I'm used to CO2 lasers from, you know, when I was in school. CO2 lasers are kind of superior in ways. They're a lot more expensive, they're a lot larger, but they have a finer beam because it's a single laser source, whereas the diodes we already covered are stacked lasers, you know, laser beams all side by side. So the kerf, meaning the width of your cut, is going to be greater with a diode laser than a CO2 laser. So yeah, wouldn't a CO2 laser be the better purchase, even if they are more expensive? Well, they are the choice of professional shops everywhere. And then let's not forget about fiber lasers. These are extremely fast, but they can only cut in a small area. And how does a fiber laser work instead of a diode laser? So we can go on the internet. We can ask people all day what they have experience cutting and how the quality differs between the different types of lasers. But I think a more interesting discussion that I have not seen anywhere on the internet is the fundamental physics behind what differentiates all the different laser types. So let's talk about how lasers work. And it comes down to a quirk of physics that has everything to do with electrons. You guys ever heard the joke that you should never trust an atom because they make up everything? Yeah, I love that one. All right, this is the diagram that we're all familiar with that describes an atom, right? So we've got these particles here making up the nucleus, and then we've got the electrons orbiting very beautifully around the nucleus. And it makes a great graphic, and you know, for school kids everywhere, this helps things make sense, kind of, but we need to forget that we ever learned that in order to make sense of anything going forward. So you do have a nucleus, and you do have electrons orbiting that nucleus, but they don't really orbit per se. They sort of exist in shells, which are, these are called valence shells, and the first valence shell can handle 2 electrons. The next valence shell can handle 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then the next one after that can handle 18. And there are, you know, mathematical reasons why each of these shells can hold as many as they can hold. And of course, the shells just keep on going. But what's interesting about these shells is if an electron gets hit by a photon. Now, a photon is a fundamental unit of light, and we kind of like to represent it like these days because it is both a wave and a particle. That's the weird thing about light. But so here, these are photons. So if an electron gets hit by a photon, it jumps shells to the next shell up. And that's a temporary condition because the electron is getting excited by the collision. And after a little while, it loses that excitement and it falls back down. When it falls back down, it releases a photon. So an electron getting hit by a photon both absorbs the photon and then releases it back. But there's other ways to get an electron excited. You can hit it with an ion. That's another particle. You can heat up the material, and as electrons get heated, they jump. Or you can hit it with electricity, and that'll cause the electrons to jump into shells. So all these electrons getting excited, they have to cool back down, you know, lose that excitement, and when they fall, they release photons. So that's the quirk, is that electrons getting excited from all the different mechanisms, when they lose that excitement, they create light. They create photons. So this is why metal that you see getting heated in the forge glows red. It's that same mechanism. Well, it can glow white hot too if you get it hot enough. And this is the fundamental mechanism that allows lasers to function because electrons release photons. But how do we get them to release so many photons that they're so intense, and also that all the photons are on the same wavelength? So normal photons, you know, you're going to get, you know, this chaos of you don't know, right? But with lasers, you want all the waves to be the same. So they all collinearly exist. This is how all lasers work right here, fundamentally. But now things get really interesting because mechanically speaking, you know, engineering-wise, how do you get these electrons excited? And then how do you make sure that all these photons coming off of the electrons are, you know, traveling together on the same wavelength, and they're so intense that they can light things on fire? It's crazy. In the 1960s, the first successful laser that was ever created was made using a rod, which I've drawn here, of pure ruby. So synthetic ruby, you know, ruby, the gem, right? And it was, you know, very well made, so it could function like a fiber optic cable, where the light, if you shine a light into this end, it would sort of bounce off the walls, and it wouldn't really cross outside of, it could. Certainly some light could escape, but not much of it did. Most of it sort of bounced off the walls. And they wrapped this ruby tube here in a, what is it, a spiral of, was it xenon or, yeah, I think it's xenon. Like the really, yeah, you've heard of xenon, the really powerful headlight technology, really, really bright lights. And this xenon tube was kind of like your old style of There's the ends, right? It's your old style of like neon signs. You think of Las Vegas, right? It was like that. And so they would pulse this xenon tube, boom, 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 and it would create extremely bright light. And that light would shine into the ruby crystal. And back to this thing, the bright light, those photons, would hit the electrons in their valence shells, which would cause them to release light from the ruby. But now the light is sort of captured inside of this fiber optic tube. So certainly some of it could leave, but most of it starts bouncing off the walls and shining out the ends, either end. Well, you don't want it to shine out the ends. So instead, what they did is they turned the very ends of the rods here into mirrors. And this mirror was 100% mirror. Nothing's coming through that mirror. This mirror up here is a 95% mirror. 5% of the electrons that hit up here get to escape, and they all have been bouncing through this rod back and forth between these two mirrors until they're so intense and they're all in, you know, the same wavelength, and they all exit that tube, and boom, you have a laser, the very first laser. And when you think about the technology that made this, suddenly the acronym laser makes sense. It's light amplification by stimulated emission of radiation. Okay, so the radiation would be the electrons. That's, you know, sense light amplification because you're taking xenon, a xenon tube, and you're creating more light, so you're amplifying that light. Okay, so it makes a lot of sense. So there's your ruby laser. The problem is ruby crystals are very expensive to make. You know what's not expensive? CO2, the gas. And so what they did is they created a tube of, you know, that can handle gas in it, and they put CO2 in there, and they also put some, what is it, nitrogen, I think, and some neon. And you could certainly use some xenon instead of the neon and, you know, the nitrogen. There are different cocktails depending on, you know, whichever manufacturer's proprietary blend of gases they've determined works the best. But the point is that the neon will glow. You've seen it all, like your Las Vegas signs, when you attach electricity to it. So you would put, you know, an electrode into this end here. We'll just stick an electrode in there, say that's a positive and say that's a negative. I think I've got this the right direction. I don't know. I don't know if it matters which one's which, but the point is you've got electricity flowing through from here to there, and the neon gets excited. So it releases light. The neon sort of excites the nitrogen, which really excites the CO2. So they could go straight from neon to CO2. That would work, but if you really want to turbocharge the effect, you put a little intermediate gas in there. So this is going to create the same thing as we saw here in the ruby laser, where we're going to start to get light shining out the ends. So once again, we put a 100% mirror here on this end, and we put a 95% mirror here on this end. So as the light bounces back and forth between these two mirrors, eventually 5% of the light comes out of this end, and it's a laser. It's all, you know, along the same wavelength, and it's very sort of narrow bound, and that is an awesome thing. But these tubes are huge. The typical ones for a laser cutter that you would buy for your home shop is going to be like 2.5 feet long. And that cannot be attached to the cutter head. So it's got to go into the back of the machine, and there's got to be a series of mirrors that get it up to the CNC head that's moving the actual beam of laser light to cut with. So pretty impractical. Also, this is a giant tube that's very fragile, and we needed better technology. Enter the diode. Dun, dun, dun. Okay, now the diode, you guys are all familiar with that name. It's an electronics device, and basically it's a bar of aluminum gallium arsenide, AlGa, aluminum gallium arsenide, As, aluminum, yeah. So the thing is, it's split into two, and it's all aluminum gallium arsenide, but there's an impurity. It's called being doped. So this half here is, you know, doped with a different impurity than this half. So this half here would be doped such that, let's just say the top valence shell was the 8 shell here, and it only had 7 electrons in it. So it wants to gain an electron. There's like a hole there. It's wanting to suck in an electron. So this is sort of positively charged. It wants electrons. Whereas this one here would be doped with an impurity such that it would have maybe all 8 electrons in this shell plus 1 up here in the 18 shell. So it wants to get rid of an electron. So it now has a negative charge. And so what we say is that this one is full of holes that want to get filled, and this one is full of things that want to fill those holes. Get your mind out of the gutter, guys. When the diode is just sitting there with no electricity being applied to it, the electrons are naturally going to wander from the side that wants to give them away to the side that wants to receive them. And what you're going to end up here with is sort of a zone here where the electrons have been given away, that want to be given away. So these are now stable here. And these holes have received electrons, so they're also stable. And now what you have is, despite the doping, a zone here called the depletion zone, where everything is back to the normal state of affairs in undoped aluminum gallium arsenide. So one way to look at this is to have all of the electrons, the negative charge, concentrated at this end, and all the positive charge, the holes that want to get filled, concentrated at this end of the diode. So if you apply a current across the diode, where the positive end is down here and the negative end is there, what you're going to do is attract these positive holes more towards the negative, because opposites attract, and all the electrons, which are negatively charged, are also going to be attracted towards this positive voltage here, and you're going to increase the depletion zone, if anything. So this is why you cannot conduct electricity in two directions across a diode. It's only one way. So this is always going to go negative here and positive here. But what happens when you do apply current like that? The depletion zone will disappear because the repelling force here will cause the electrons to now want to push across even further, and the positive charge here, the holes, are now going to move down that way. The act of the electron leaving the hole is what we talk about here, where it's basically jumping a shell, a valence shell, and it releases a photon. So that's why LEDs exist, light-emitting diodes. How can you turn an LED into a diode laser? Well, that's where things get interesting, because you add a very thin strip here in the middle of some other semiconductor. So as these photons are being released, that light gets captured here in this semiconductor, and it bounces off the walls in the same way that it was doing in the fiber optic tube of the Ruby laser. And then we also put a mirror, 100% mirror on this end, and a 95% mirror on that end. So very microscopically now, we have a tiny little laser tube which outputs collimated light intensely out this end. And voila, you have a diode laser. It's solid state, it's very small, there's no mechanical things that can go wrong. This is a total winner as far as technology goes. This basically represents the dawn of the technology, and the CO2 laser is kind of like your vacuum tubes. Think of your old stereos from the 1970s or something like that. So we are now firmly into semiconductors and solid state stuff when it comes to our lasers. But there's one more type of laser that we should talk about, because it's a machine that you can go buy today for primarily used for cutting metal, or at least etching metal, and this is called a fiber laser. And a fiber laser is just basically a diode laser with a whole turbocharging system put on top of it. So in our example here, we're just going to use a single diode laser, but of course, like we talked about before, you could have multiples and mirrors so that they all, get the beam of the lasers lined up and whatnot. Anyway, this diode laser is going to be shining down a fiber optic cable. And so the fiber optic cable is going to loop around and around and around and then pop out over here. So I'm just going to draw it with some thickness up until that point, and yeah, we'll get the, you get the idea. There's thickness all the way through the loop. But this fiber optics, it's not a normal fiber optic cable where the light just bounces off all the walls. It has sort of an inner fiber optic cable going there as well. And that inner fiber optic cable has some sort of like doping kind of a thing going on. It's not exactly doping, I'm greatly simplifying here. But basically, as the diode laser light enters into the fiber optic cable and bounces around, it's going to cross the core from time to time, and the intense laser beam is going to activate, it's going to amplify even more so the electrons are going to get excited inside of this core, which is going to create more laser. Now you have to have a very long fiber optic, which is why it's looped, because the effect is pretty weak. You couldn't make it happen in a short distance, but that's basically how you amplify what's already light amplification, and it's doubly amplified now, and that's why you get such an intense beam out that end that you can cut metal. So diode-based lasers, straight diodes and fiber lasers are where all of the exciting advances are coming from. It's a wonderful time to be a part of this technology, but you can't dismiss CO2 lasers. They have one major advantage that I don't know will ever be taken away from them. That being wavelength. Okay, a CO2 laser functions with a wavelength 10 times longer than the longest wavelength you can get out of a diode. And that means, like for instance, cutting acrylic, CO2 lasers can cut it with zero charring on the edges. There's no burned edges. And that gives it the ability to be glued with a solvent, like a highly potent solvent, to be glued to another piece of acrylic in such a way that you don't even see the seam. It's incredible. And we're probably not going to get there with diode lasers. So, just in the same way that some people still listen to vacuum tube amplifiers, this is mine. I love the way it sounds using this antiquated technology. And yeah, CO2 lasers will probably be the professional choice into the far future. Let's talk about the software you will need to install on your computer in order to run the laser cutter. It's called Xtool Creative Space. This is what it looks like. To install it, you simply go to the xtool.com website, click on the software menu item here at the top. But once it's installed, it's not that intuitive if you've never used something like this before. So Xtool has this support.xtool.com portion of their website where they've got all these tutorials, and man, there are a lot of them. So thinking I was going to go through every one of those tutorials, I opened up each of these links in a separate tab in my browser here, and you can see that each of the links has its own sub-menu. Like, this is intense, you guys. And reading through it, it's really not user-friendly. This seems like it was written by the same engineer who wrote the software itself. And as we all know, the people who are geniuses and quite capable at writing software should not be allowed anywhere near the customers because they just cannot think or communicate with human beings. It's sort of two different skill sets. Xtool should absolutely hire a technical writer to improve upon this. And even more than that, they need a quick start guide because it's really not that hard, you guys. So in the interest of serving the community here, I'm going to provide the quick start guide. The first thing you want to do is connect the laser cutter to your Wi-Fi, most likely, so that you can run it through your printer without your computer being tethered to the machine. Now, the first time you set the machine up, you will need to be tethered with the included USB cable. Once the two machines are connected, you can go up to here and connect to the machine. It says disconnect right now, but you would connect to the machine if it doesn't do it automatically. Now, you need to click right here next to this Xtool over here on the right. This is bad UX design, in my opinion. These two should not be separate. Look at, they're both pictures of Xtool. They both say Xtool. This should be the same menu. You should either get to it up here, and in fact, I think all this functionality should be happening right here. So yeah, click the little gear icon like normal, and then here in the basic info is where you are supposed to, according to the instructions, be able to assign the laser cutter to the Wi-Fi network in your office or your home or whatever it is. But I don't see the Wi-Fi interface here. Clicking on the working info, I also don't see it here or there. So this was a big frustration for me until I noticed this little clue. See the little tiny numbers poking up at the bottom? Oh, you can scroll. There's more items down below here. Again, very bad user interface. There should be an arrow here with a scroll, the typical scrolling thing, and it's not there. So going to this menu, this looks perfectly like complete, but nope, there is hidden functionality down there if you scroll. Plug in your Wi-Fi credentials there, and the laser cutter will now be on the Wi-Fi network, which means you can walk across the room like I am here to your main tower computer and run the laser cutter from across the room. So now that the software is installed and the laser is connected to it, what are you going to cut? Well, you can certainly use the tools that they give you right here in the program to to generate some geometry. You can draw boxes. You can use this pen tool to draw curves, splines as they call them, technically, not curves. And you could cut that. But it's very basic functionality, you guys. And I would not use this unless you're just being artistic. There are much better ways to generate line work for cutting. And if nothing else, use LibreCAD. I've found this to be a very functional, completely free, lightweight, just a great all-around two-dimensional CAD platform. If you're using Onshape or Fusion 360 or Rhinoceros 3D, that's my CAD platform, or FreeCAD, doesn't matter which. What you want to do is take your two-dimensional drawing and export it to a DXF format. That's Drawing Exchange format. And then here in the Xtools Creative Space software, you click on the X up here, the little drop-down button, you have File, Import Image. Even though it's not an image that you're importing, you can see right here the different types that it will accept include WebP, DXF, and then all of the visual image formats. So I have this line work from another project. So when nothing's highlighted, it's not obvious how you proceed, but you can just click on the line work that you want to assign properties to, and up pops this Easy Set panel, which gives us two parameters. These are pretty much the only two parameters in laser cutting, and that is your speed and the intensity of the laser. So they call that the power percentage. And the speed is, in this case, I'll get to it in a minute, pretty much I would not go above like 35% for cutting outlines. And then, so you pretty much only have one variable that you can play with on this machine, and that is the power level. But this machine does have a fancy bit of functionality, and that is the ability to drop down a certain distance with each pass. So if you're cutting thick material, you'll need to cut and then cut again and make multiple passes at it. And if it drops down, the focal point will drop down with it. So it'll start cutting at the bottom of the last cut, but in focus, which is a nice functionality to have. So I'm just cutting some office paper here for my first test cuts. And I'm just going to set that at 50%. And like I said, speed at about 30. And then you click on Go to Process. Now, before you start cutting, you need to focus the laser. Think of the magnifying glass that you played with as a kid for burning leaves or whatnot. If the light circle is too big, it's not hot enough to burn. And so you need to be just focused perfectly to get all that intense energy into the smallest possible circle. And that's how you cut effectively. So this machine auto-focuses itself using the BL Touch sensor that we already saw. And the way you activate that sensor is by clicking the little ruler icon right here. But first, this little red plus sign needs to be positioned over your material. So it would be great, again, user interface stuff, for me to be able to click that plus sign and drag it over where I know the material to be, or to use the arrow keys, or to have a whole other button here that has the jogging commands where I can manually in the software move the laser cutter to where it needs to be. None of that is an option in this software because it's still in beta, I guess, although it's been more than a year. So it's really kind of unforgivable in my book. Software is self-functional, but this is really lacking. So what I have to do now is walk over to the machine and physically move the laser head over the material. And I have to admit, even though the functionality to move the laser is not built in to the software here, it's pretty cool that even when the machine is sort of powered down, the closed loop steppers keep track of the absolute position of the cutting head. So here I am physically moving the cutting head, and you guys should have seen the little red plus sign on the screen moving along with that. Now we go to this distance field and we click the little ruler icon. And it automatically determines the focal distance for us. Next, we'll highlight the geometry and then click framing. We'll get that beep, which tells us to come over here and press the button, and we can watch the plus sign draw an outline of where our cut is going to happen. So our cut's going to happen way up here, and that's wrong. So we can either move the stock material physically, or we can move the geometry in software to correspond with where the stock material is sitting, and then test the framing one more time. That's better. Now we close the lid, turn room ventilation on so that it can suck the fumes out of the back of the laser. Click here on Go to Process, and we could press this play button right here to simulate the movements, but it's really silly to have that functionality built into this. It's overkill. That's a functionality from the CNC world when you're cutting and you need to preview your cuts, but not here. So we can just click on Start. Then back here at the printer, we click the button and watch it cut. The air assist unit here is vibrating, which means there's a nice jet of air coming out of the aperture there and preventing any soot from building up on the lens. Pretty cool, you guys. Cutting 0.1 millimeter thick office paper is about the easiest job you can possibly do with a laser. I should be able to fly through this cut. So let's run it as fast and as hot as we can. In my experiments, this is about the right setting. Look, some of these pieces got fully cut through and even blown out of place by the jet of air coming out of the aperture there. But other pieces are still firmly attached. You can see all through there. I'm actually lifting up the whole page rather than detaching it there. Why is it that we're getting an inconsistent cut, especially on such thin stock material? The answer, if you're familiar with 3D printing, should not be surprising to you, and that is acceleration and jerk settings. This laser head that we disassembled, we saw it has some serious mass to it. There's a chunk of aluminum there that's been CNC cut. There's some fans. There's all this external stuff on there, and that means that you cannot take this head and instantly go from stationary to moving at full speed. There's a ramp up. This line here, right in the middle there, it got up to the full speed that we had it set at, 220 millimeters per second or whatever it was. But across here, where it cut through, it didn't have enough length to reach full speed, so it was traveling slower. The cutting should happen at a single speed, and the software should somehow do some fancy math to compensate for the difference in speeds that will be achieved based on acceleration. In my experiments today, I found that reliably, to get a constant sort of speed on this particular cut, I did not want to exceed 36 millimeters per second, so 10 times slower than the machine thinks is the maximum speed. Cutting out that pattern on this very rubbery anti-skid material with a 3M adhesive backing, and there's a lot of smoke that's made from burning both the backing as well as the rubber, so I'm glad that my vent solution is actually functional here. There's a slight smell of smoke in the room, and then on the next cut, look at all the sparks that the laser beam hitting the silicone carbide created. And yeah, these are the final result. So separate it from the backing paper so that I can now stick it onto the 3D print. So now we can see what this project was all about. I'm wrapping a complicated shape, a three-dimensional handle, with a two-dimensional grip tape. And I wanted to get a feel for each of the different styles of grip tape. These two here are 3M products. This is basically sandpaper. It's like skateboard grip tape on this one. Pretty rough on the hands, but yeah, really grippy. This is, I don't know, some sort of like sailboat, soft, rubbery grip. That's this one here. I think it's called Safety Walk. Yeah, 3M Safety Walk. And this one, I kind of like the best. It feels really thin. It's just sort of rubbery. I don't remember where I got this or what it is. These were my previous attempts at getting a good pattern that wrapped around the handle well. And what I was doing for these is spray gluing them to the back of the grip tape like so, and then painfully cutting them out with a knife. It would take me like an hour for each try. And that was just ridiculous. So very nice to have this tool at my disposal now. I can do in like, what, 2 minutes? What used to take me an hour to do. The Ozark Trail branded 7.5-inch folding knife that you get at Walmart only costs $10, and all of the everyday carry guys on the internet, the knife nerds, are super stoked on this because it's got D2 high carbon steel, which is a really high quality blade material. So yeah, this is a nice knife, but I don't really care for the orange color, so I want to make some new scales out of these denim swatches that I cut from an old pair of jeans. I'm going to use this epoxy resin to laminate these pieces of denim together. I'm going to do it like that. Put it in between these two pieces of plywood, put a clamp on it, and if it goes right, this will be a really nice piece of micarta in the morning. I taped the knife scale and a ruler to the front of the machine and then took a picture from across the room with this 100mm lens for the least amount of distortion. Bringing the distortion-free photo into CAD, I'm able to size the photo here in the program so that 30 centimeters in the photo equals 30 centimeters based on the scale of the CAD drawing. And now the orange knife scale will be to scale. The scale is to scale. Anyway, so I'm able to trace it. You can see what I've done there. So now I can export that tracing as a DXF, which I then import into Xtool Creative Space. Let's see how accurate this first go around is. Hey, that's not bad at all. This radius right here is about the only thing that I messed up on. Looking from the back, we don't really see any orange poking through either. Fix that and I'm ready for the final cut. The micarta is in the machine on top of the test paper just for alignment. There's the test cuts up there and this should work, so let's see what it does. We're doing 4 passes and each pass drops by 1mm. Compared to 3D printing, it's a whole lot faster to complete the job when you're laser cutting. Ta-da! Now I've just got to do some sanding and some other finish work. One thing I didn't count on when I was conceptualizing this project is the pocket on the back here that's needed to clear the spring there. So I had to use my Dremel Router attachment. You can see all the fuzz, and I routed out these pockets. They aren't pretty, but they do the job. So that sits on there nicely now, but only the very tip of the slide lock can I catch with my finger. It's a little bit uncomfortable, so I'm going to carve a little recess right there, just enough to be able to grab it more easily. So my old work pants are now my new work knife. Very functional. It was a lot of fun to do as a project. There's one more issue we should discuss in regards to this machine, and that is how thick of a material can you reasonably cut on it. We've got this plywood that they sent us that's about 1/8 of an inch, and this smoky acrylic. So it's black colored. You can barely see through it. There's almost no light that passes it. Clear acrylic, one more time, it will not cut clear acrylic. This slate here is thicker, and my apologies for not doing any projects with these. You can see laser cut artifacts like this all over Etsy. And if you're planning on getting into the Etsy game and selling on Etsy, this would be a great machine to do that with. So yeah, all of these materials are possible, but how thick is the maximum material that you can cut? In my judgment, I would say it's about 1/2 an inch. But you can do more or less, you know, depending on what you're trying to accomplish. You'll need to play around with it. There are other variables than just saying there's a hard limit at 1/2 an inch. Kerf generally refers to the thickness of material that is removed when you're cutting. But in the case of a laser cutter, the kerf is not straight up and down, and that's counterintuitive, right? You think of a laser beam as being parallel light. So when it gets to the material, it's going to cut a parallel path through that, right? That's what you think. But it's not the case, because remember, we had, what was it, 6 lines that are all coming to the aperture, and in the aperture, there's a lens, okay? And that lens focuses 6 lines getting ready for the cut. This is the focal point right here, and that's where you want your laser calibrated so that the top of your material basically is there. So if you had a sheet of paper that's very thin, the cut is all going to be happening right there on the surface, right there at the focal point. But if you went with a sheet of plywood, for instance, what you're going to get is this area being cut out, and you can see it's angled, right? It starts out small and it gets wider as it goes down. Well, you could focus it so that you're, you know, half on and half off the plywood, and so you'd have sort of an hourglass shaped cut. But these are issues to think about. The ability of the laser to cut through materials is greatly diminished when it's away from its focal point. And remember, this machine can do depth passes, so it can drop the laser down like 1 millimeter for each pass. So let's say our laser beam looks like this, and we start our cut on some plywood, which is of thickness like that, and it's perfectly focused in the beginning, and we cut down 1 millimeter. So we get a nice single line. Well, the next millimeter that we're going to need to cut, right, we're going to need to bring this thing down, this light down, to cut it like so. So for that next bit of cut, we have this out of focus blocking the light. So that is a significant portion of your laser beam before it's focused that's being blocked by material up above. And so this is getting kind of charred, and it's not going to be very clean. And the deeper you go, the wider that nasty char thing becomes. So as a rule of thumb, with this machine, I would say don't try to cut anything thicker than 1/2 inch or 13 millimeters. No matter how hard I try, I can't get the dust off this shirt from sanding on the micarta here. But hey, I digress. During the course of filming this video, I was reminded why I love laser cutters so much. And it's because they're very hard to make a mistake while using. You might get your settings a little bit wrong here or there, but nothing catastrophic is going to happen, and you get the results of your project lickety-split. So low stress, instant gratification, yeah, that's a recipe for enjoyment. I highly recommend that you go get one of these, the X-Tool S1. This is the machine to get. Watch the other videos, read the other reviews. It's pretty much unanimous. X-Tool has made something special here. And if you're going to get one, once again, like I said in the intro, please follow the link in the description, do the whole affiliate marketing thing, and help out this channel. But yeah, I understand that $2,000 seems like a lot of money for a machine. But let's put that into context. Just, I don't know, 2 years ago, you had to spend $10,000 to $15,000 to get this functionality by purchasing a CO2 laser. Now a CO2 laser, as we covered, it's a better laser, but it's 5 times the price. Is it 5 times the capability? No, this is like 85% of the way there. So value-wise, bang for your buck, this is definitely the machine to get. And if you can find a use for it, now's the time. This is a magic moment here for laser cutting, and I'm stoked to finally have one at my disposal again. It's been 10 years since I was able to use one in my master's program. So yeah, these were projects that I was actually working on, and I really did need laser cutter functionality for this. So I'm happy as can be, you guys. I can't say it enough. I really like this machine. So thank you so much for watching. Have a great day. I'll see you in the next video.